Alright, so welcome back to particle physics and the Standard Model. This is lecture 43, and last time we successfully identified a basis invariant way to a basis invariant measure of CP violation in the weak sector, which was what? The Yarlskog invariant. So we had written it down in the lecture before that, but I showed to you why it is indeed invariant. How did that come about? We saw that this Yarlskog invariant was nothing but twice the area of the unitarity triangle, right? That is what we have written down here on the Argand plane, that is the geometric interpretation of it. And then its invariance could also be seen by actually writing down the the orthonormal relations between the rows and the columns of the CK matrix, and by manipulating it suitably we did find that each of these quantities that we wrote down here as the Yarlskog invariant, there are totally 6 combinations, remember, all those 6 combinations were indeed the same, okay. And from there on we moved on to the neutrino sector, and immediately we see that since you can only handle the flavor eigenstates of neutrino sectors, you get a spectacular phenomenon called neutrino oscillations, going by a better name of mass induced flavor change, okay. And that basically comes from the fact that you have the PMNS matrix that rotates you from the mass basis to the flavor basis, and that it is the mass basis that evolves according to the Schrodinger equation, okay. The Hamiltonian makes the mass basis evolve, so that generically the propagating eigenstates or the mass eigenstates need not align with the flavor eigenstates, right. We see this all the time in quantum mechanics, we are seeing it in a particle physics context here, right. You can have 2 different eigenbases, but here we are seeing it with some physical meaning, okay. That is what it is, there is a mismatch between flavor eigenstate and mass eigenstate, so that if I prepare a neutrino in some flavor eigenstate and let it propagate, in general I may not measure it again in the same flavor eigenstate, okay. So that is what we have been trying to work out here. How did that come about? I could write the flavor eigenstate as a superposition of 2 mass eigenstates like here, then as it evolves with time it is the mass eigenstates that pick up this e power minus I px phase, right. So I can call this combination some you can call it whatever, I just like to call it nu e of t within quotes just to indicate that is nu e of t is nu e of 0 is where this started from. Then what did we do? Neutrinos are in most contexts highly relativistic. So in this 4 vector product you can take the energy, you can expand the energy in terms of the momentum, taking the momentum to be in the z direction, and I get Pz plus m nu squared over 2 Pz as the energy, right, and then or 4th order terms which I neglect. So I plug that back into the evolution, okay, and I end up with the evolved eigenstate being cos theta, which is the mixing angle, times e power I m1 squared L, where L is the distance travelled by the neutrino divided by the energy of the neutrino. That is the coefficient of the nu 1 state, and then you get a similar coefficient with the sin theta and m2 squared for the nu 2 state, okay. So where are we going with all this? Okay, we see how the state actually evolves, but in quantum mechanics we just do not look at the evolution of the wave function, we actually measure probabilities, right. That is indeed the bridge between the deterministic quantum world and the deterministic classical world, right, these probabilities, right. And of course we know how to get the probability. We take the inner product and square it, right. So let me write down the notation and then I will explain exactly what this is. What am I doing here? I am asking what is the probability of measuring this evolved state okay, nu e of L within quotes, what is the probability of measuring that as the electron neutrino that you started out with? Okay, is that clear? So just to make this point, just to drive home this point, it also means I can also think of a probability that I started out as an electron eigenstate, like you prepare your flavor eigenstate this way, okay, through some particle beams, you hit protons, you hit a proton beam on some target, you get some pions, let's say, and the pions decay to neutrinos. So you prepare neutrinos in this state, okay. So I start with that. After it propagates, I can ask what is the probability that I detect it back as a muon neutrino, okay. So how will I write that? So I start as an electron neutrino, and I ask, oh, I'm sorry, so that's not how I should be writing it. So I started as an electron, an electron neutrino, so that after evolution, it has become, after propagating and evolving, it's still now in this state. That's what I've written here, right? So I'm asking now, okay, there's a ket here. So I'm asking what is the probability that I'm detecting this as a muon neutrino. That's what PE nu stands for, okay. Similarly, I could have started with some muon neutrinos flavor eigenstate, right? So let me write that also down. If that were the case, I can ask what is the probability that I detect it as an electron neutrino now, okay. So that I would write like this, where suitably I would find an expression for mu nu of L within quotes just by following this procedure over here on the right, okay. And finally, to finish the quadrant, I can start as a muon neutrino and I can ask what is the probability that it's still a muon neutrino now, okay. Simple. If not, go over this again and familiarize yourself with these concepts, okay. It's very important to understand the physical meaning of what we are doing here, okay. Okay, so now let's go back to blue color and ask what this is. How would I write this? I have now expanded the nu e of L within quotes in terms of this basis, right, nu 1 and nu 2, which is the mass basis. So might as well use the same basis for the unevolved state. So this is nothing but nu e of 0, right, where I'm writing the time label here, right. So and we know that this is 1, this is 0, right, and this is 0, and what else? This is 1, correct. This is a normal basis basically, correct, orthonormal basis rather, right. So I'm going to make use of that to get that sandwiched probability is, there's a 2 here, 2e, okay, plus sine square e power minus m2l over 2e absolute value squared, okay. Was that clear what happened here? I took the cos theta here, hit it with this cos theta, that's why I get a cos square theta, and then I hit the sine theta with this sine theta, so I got a sine square theta, and the other terms basically go to 0, and then I just, the e power I terms just go for a ride, okay. Now further I can simplify this to write, okay. So this simplification I am not going to do now. You go ahead, expand this, you know how to do a square plus b square, but this is just with the absolute value. These are complex numbers. Do the expansion, simplify it, okay. Take out, there will be a cos square theta plus sin square theta whole square, etc., right. Put all that in correctly and you will find that the probability that I get it back as an electron neutrino is this, okay. This is an expression you should never forget, okay. If you forget it, you can easily derive it, okay. We will see many consequences of an expression like this, alright. Now what is delta m squared here? I will first tell you what it is not. It is not delta m1 minus delta m2 whole squared, nothing like that, okay. So rather, sorry, it is actually not, so it is not this obviously, because delta m1 makes no sense. It is not m1 minus m2 the whole squared, okay. What it is delta of, it is actually delta of m squared, okay. In other words, it is, the way we are defining it is m2 squared minus m1 squared, okay. So how do we see that? See, I have an m1 here and an m2 here and then I square it, right. So correct, and then in the absolute value squared, I add up these terms, or sometimes I subtract these terms and then I get the sign, correct, and eventually I will end up with exactly this, okay. Alright. So from this, one thing should be obvious without having to derive it. You can convince yourself that P mu mu P should be equal to PEE, okay. That is clear here, right. There is a symmetry about this, right. There is nothing here that really says it is only the EE that you are picking up here, correct. So the theta is the same over here, delta m squared is the same, none of this depends on the exact flavor that we are looking at here. We just look for, if you start with the flavor, what is the probability you get back the same flavor, okay. Of course, by the law of probability, that probability should add up to 1. The probability that I detect something as a muon neutrino after starting as an electron neutrino is 1 minus PEE is what I meant, okay. And similarly this, okay, good. One more thing to notice here is what happens when theta goes to 0. That implies P equals P mu mu equals 1, right. That is, if there is no mixing over here, then the flavor eigenstate is the mass eigenstate, that is all it means. So the propagation eigenstate is still the same. You are going to recover at any point in time or any point, any distance away from the source, basically you are going to recover it as the same flavor, right. So this would also mean obviously that there is no conversion among the flavors, okay. Another thing, when delta m square is 0, it is the same, right, because the sign here goes to 0, correct. Again, why is that? That is also because ultimately if the masses are the same, right, if m2 square is equal to m1 square, then there is no differential evolution between the two eigenstates, right? Even if you start with this mixture, okay, even if the electron neutrino is a mixture of nu1 and nu2, nu1 and nu2 are propagating at exactly the same rate, right, over here, right? That is what we end up with in the end, right? So, if they evolve at the same rate, the cos theta sin theta admixture is preserved during propagation, correct. So, there is no oscillations, there is no conversion of flavor that you would see when you measure the flavor eigenstate after propagation, okay. So, all these give us confidence that this formula is indeed correct, and obviously if L is 0, there is no propagation, so there is no conversion and so on, okay. Now, I am going to write down the formula for 3 flavor oscillations. Why? Because in nature we see 3 flavors, right. Up to this point we have been using a toy model with 2 flavors, correct. So, the probability for conversion between flavors with 3 flavors, I am going to write it down. I did not derive it because it is not that trivial to derive it, but who is going to derive it? Of course, it is going to be you, right. So, it is not trivial, but it is not that hard either. It is a bit tedious, but it is extremely instructive to go and derive this, okay. So, I am going to write down the expression, okay, but you are the one who is going to really derive it. The 2 by 2 matrix contains just an angle, rotation angle, but now we have a 3 by 3 PMNS matrix. So, I am going to write the probability in terms of the PMNS matrix elements, okay. So, let me just write this, U is UPMNS, okay. Again, Greek indices stand for flavor and Latin indices stand for mass eigenstate, okay. So, it is this plus 2 times, this is a compact way to write it, there are other ways to write this also, U alpha j star, U beta j, U alpha k, U beta k star, okay, and cosine of delta m j k squared L over 2 E nu, the energy of the neutrinos, minus there is a phase here, okay. It is an interesting phase. The phase is nothing but the argument of this combination of complex numbers. U beta k star, okay. So, I suggest the first task for you as set one of the you let us just call it alpha I to 0, okay, to get the 2 flavor formula, the 2 flavor probability. So, you start with this to build some intuition, then try to derive this yourself, okay. It is not that hard, we just used all the concepts that you need are already here. So, that was for the sake of completeness. Let us move on to more nice physics here, okay. So, let us inspect how one could plot P mu nu, and let us try to understand a few physical things here, okay. P mu nu as a function of L basically, okay. So, what is P mu nu? P nu rather, that is you start as an electron neutrino, you detect it as a muon neutrino after distance L. What is that? We just saw it's 1 minus PEE, right? To conserve probability, unitarity. So that's just this. Yes. Now, how should I plot this as a function of L? It's a sine square, correct? That means I would plot it like this. Yes. Okay, very good. Now, what is the amplitude of this sinusoid? Is it 1 because it's a probability? No, not really. The two probabilities of PE mu plus PE add up to 1, but this probability alone does not have an amplitude 1. In fact, the amplitude is this, right? Sine square 2 theta, correct? That is what you are having a sinusoidal in L over. Okay, so let me indicate that with this. So the amplitude is sine square 2 theta. Okay, that's one thing to note, that your probability is never going to exceed sine square 2 theta, where theta is given to you by nature. So let me just write that. So theta given by nature, because this is not in your hands, right? This is a theta that is determined in the Lagrangian level itself, correct? This theta over here. Okay, now the real fun is to identify over what length, okay, you complete one oscillation, about one oscillation. Okay, it would make sense to call that some oscillation length, right? In this case, what is the oscillation length using this formula? It is obviously something that I can pick out from here, correct? So in other words, I can now rewrite this as sine square 2 theta sine square L over some oscillation length. Okay, and in fact, to make things look a little cleaner, we normalize it with the pi outside. Okay, and what is this L oscillation length? LOSC, the oscillation length is 4E over pi delta m squared. See, I just rewritten the equation above. That's all I've done. Okay, that's where all the 4 and the pi and everything come from, which tells me that the reason I pick out this particular length factor here, right? First of all, see if the units work out. This is a length. On the right hand side, I have an energy divided by mass squared, right? Energy over mass squared has units of length in natural units. So that works out. We are setting C to 1, so don't get thrown off by that. Okay. So this basically gives us an idea of where the probability peaks. Okay. It peaks at 2n plus 1 over 2 times the oscillation length. That's the reason why we talk about this quantity at all, where n is of course 0, 1, 2 and so on, right? Take 0, that just means I have L as half times the oscillation length. If I put that in, I get what? Sine square pi over 2, which is 1, correct? So that's a point where the probability peaks, correct? So why is this useful? Because if I pick my, if I choose L close to, the oscillation length, let's say over 2, then I have a better chance of seeing flavor conversion, right? If you want to measure an effect, better go to a place where the effect is at its maximum, right? So that's what we are trying to do here. So sine square 2 theta is not in your hands, that is given to you by nature, but at least this is in your hands, correct? So let me write that. So I wrote that theta given by nature, so I am going to write here L is set by you, rather by the experimenter. You can decide at what distance down the source you want to measure the conversion probability, okay? But it's not just in experiments made by humans. This turns out in certain cases to be very fortuitously, luckily, the correct distance to measure some fundamental parameters like delta m squared and theta also, okay? So we are going to get into that right away. So I am going to say that using, let me just quickly write this so you understand what I am saying here. Using the right sources of neutrinos and right baselines. I have introduced a word here. Baseline is nothing but L, okay? So I kept saying length, but the word people use in this context is baseline, okay? We got by measuring, let me also put this, and measuring probabilities, okay, of one flavor converting to other. What else is left? We got this, we got this. So you know, we got the L was at the right baseline around the oscillation length, right? By seeing the highest probability conversion, right? What else is left? And we also know the energy. So the sources, right sources meaning the right energies for the neutrinos. Okay, so we have this, we have this, we have this. This doesn't matter here. The theta doesn't matter because we are looking at the maximum probability anyway. What is left? Delta m square is left, correct? We got delta m squared between the first and the second mass eigenstate, but also delta m squared between the first and the third mass eigenstate, okay? And what did we get? We had, these are numbers that are, you know, in physics you do not have to remember all the numbers, but there are certain numbers that are very good to keep in mind, and this is one of them, okay? Delta m12 squared was measured to be 8 times 10 power minus 5. What is the units here? It's electron volt squared. It's a mass squared, right? So in electron volt squared, what I have written here is just nothing but the error bar, okay? On 8 you have a 0.5. So, and delta m13 squared was measured to be 2 times 10 power minus 3 electron volt squared, okay? I do not remember what the error bar is, does not matter, you can check it, okay? Now, what were these experiments? What were these sources? What were these baselines? How did they make this measurement? So that's just what we are going to see in the next class. So now I'm just going to wrap up by saying that this measurement, the first one, comes from measuring neutrinos made in the sun. So this is sometimes called delta m squared solar, and This next one comes from neutrinos made in the atmosphere of the earth. So this is called delta m square atmosphere. So solar neutrinos, atmospheric neutrinos. So in the neutrino world you will keep hearing these words again and again. Okay. So I will stop here. In the next class we will see exactly how these measurements were made, what baselines were used, and we will understand the sources also. Okay. Thank you. See you in the next class.